Okay, problem 4. The figure at the bottom of the page shows a plot of a potential map made by a student, but the distance scale is unknown. Lines are drawn at 1 volt intervals. The student determined that the electric field at point X has a magnitude of 100 newtons per coulomb. How far apart are the adjacent equipotentials? Okie dokes. So, starting off, we're told that at this point X, the electric field is equal to 100 newtons per coulomb. We could also choose to use the units as volts per meter instead. As well, we know that the potential difference between these lines are 1 volt each. So that means our delta V is equal to 1 volt. So the equation we want to use here is going to be E is equal to negative delta V over delta Z, which is just the same exact equation as negative V over D. It's just a different way to write the potential difference and the distance. So what we're going to do here is solve for delta Z. And we're going to get delta Z is equal to negative delta V over E. Go ahead and plug in. It's going to be 1 volt here divided by 100. I'm going to use volts per meter so that the volts just cancel out. And we're left with 1 over meters, which is just going to get us a meters up top. And so that's going to become 10 to the negative 2 meters, which if you wanted to, you can convert this to centimeters, and it comes out to exactly 1 centimeter. Okay, so that's part A. Moving on to part B. If an electron was placed at point X, how large a force would it experience? So for this, we're just going to use F is equal to QE, which is an equation we used a bit last week. We're just going to plug in for the charge of an electron, which is negative 1.6 times 10 to the negative 19 coulombs times our electric field. In this case, I'm going to use the newtons per coulomb unit so that our coulombs will cancel and just leave us with newtons, which is perfect. And so, of course, we'll be left with negative 1.6 times 10 to the negative 17 newtons. As well, I accidentally dropped the negative here. Really, the negative for part A doesn't really so much matter, right? Because we're just finding the distance between these lines. So there's really no inherent reason to care about the direction. So that really wouldn't change our answer too much, but it's good to not drop negative signs. Okay, moving on to part C. In part B, which way would the electron move and why? So, if the electric field is pointing to the right, as indicated by our arrow, that means an electron placed at X, right, is going to move in the opposite direction. It's going to accelerate in the opposite direction that the electric field is pointing, which means our electron placed at X will move to the left. Okay. As well, moving on to part D, if these potential lines are caused by an isolated charge at the center, is it a positive or negative charge and why? So there's really actually a couple of ways we could go about this. We know that the electric fields produced by the charge, if the charge is creating these lines, any electric field produced by a charge, if that charge is negative, then the electric field produced will be towards that charge. Alternatively, if the charge is positive, it has the opposite effect, and the electric field would be pointing away. So in this case, we have the electric field pointing towards the center, where our charge is located, so we know that the charge must be negative. Another way you could arrive at this negative answer is by looking at what happens to the electron that we place there. Which, if we place the electron, we know it is repelled from the center charge, which means that the charge must be a like charge and also must be negative, because like charges repel, whereas opposite charges attract. Okay, so that's problem 4.